All right, so now we're ready to actually take a look at steps for solving related rates word problems and see some examples. So steps to go through, and these are just some ideas. You're going to develop ones that work for you. But some ideas to think about would be to identify given quantities, so information that they're already just coming out and stating, and then determine what you need to find, so what they're asking you to do. A nice suggestion there would be drawing pictures so that you can have something to label. Then you have to write an equation that involves the variables that you're talking about. Substitute any constants into the problem. And we just spent time talking about what's a constant versus what is changing. Do not plug in a variable that's changing. You cannot plug them in to start with, or it throws off all of your derivative calculations. So we look at what we know, we look at what we want to find, we write an equation that involves those, we plug in any numbers that aren't changing, and then this one is just not always something that you want to do, but you want to try to end up with an equation that only has two variables. So maybe make some substitutions, rework it a little bit if possible, just so that your derivative work is a little bit easier. The more variables you have, the more complicated your derivatives are going to be. So we get it all set up, and then this whole implicit idea is that we want to differentiate both sides implicitly because we're talking about with respect to time. So they're going to say find the rate of change of this with respect to time. And at that point, plug in anything that is left and solve for what they're asking. Solve for the rate of change that you need. So let's see what that looks like in a problem. Okay. And I always have the original problem over on the left. Leave that unmarked so that it's a good study guide for you if you want to fold over and actually quiz yourself later. And then we have the problem over on this right side where we can mark it up. A pebble is dropped into a calm pond, causing ripples in the form of concentric circles. That's nice, so I know what's going on. Not really key to me solving anything. Then they talk about the radius, r, of the outer ripple is increasing at a constant rate of 1 foot per second. When the radius is 4 feet, at what rate is the total area of the disturbed water changing? Well, now we get into what they want. So when the radius is 4 feet, they want to know at what rate is the area of the water changing. So we want, well, with respect to time, the area changing would be dA dt, when specifically they said the radius was 4. And that first information, the radius is increasing at a constant rate, so dr dt, the radius is changing with respect to time, at a rate of 1 foot per second. Okay. And when the radius is 4 feet, so it's nice that my units are matching up. Okay, well, I have information that I know in blue, and I have information that I want. So you want to see if, can you come up with a formula? Since you want dA dt, can you come up with a formula for A with R in it? Oops. And so you just have to think about a formula for area of a circle. Okay, well, area of a circle is pi r squared. Well, yes, the area formula involves r. And kind of talking about the steps on the last page, they said it's nice if you have two letters. We do. We have A and R, so that's nice. We want to think about if anything is constant, but these are concentric circles. They're getting larger and larger and larger. Nothing is constant in this situation. So I want dA dt. I am ready to start now differentiating with respect to time. Differentiate with respect to time. So derivative of A would be 1, but it's implicit, so 1 dA dt. Derivative of A with respect to time. Pi on that other side is a constant, so it's going to hang in front. When I go to differentiate r squared, 2r, but with respect to time, dr dt. That's an implicit idea as well. So I've taken my derivatives, and now I want to take the information I know and plug in so I can answer the question. So I know that dr dt was 1. I know that they're interested when the radius is 4. And then I have my 2 pi just from the problem. So I know dA dt specifically when r is 4 is going to be equal to 2 times pi times 4 times 1. So 8 pi. And then looking at the units, if you go back to the notation, dA dt, well, area would be changing, or area would be measured in feet squared, and then time would be measured in seconds. So the rate of change label should be feet squared per second. 8 pi feet squared per second. Looking at another example. A rangefinder tracks a hot air balloon rising straight up from a level field 500 feet from the liftoff point. Well, in this case, we've got some information given to us in that first line. We've got a hot air balloon rising straight up, the field is level, and we are 500 feet, the rangefinder is 500 feet from the liftoff point. I'm going to start drawing a picture of all that. So balloon is rising straight up. It's a level field, so I'm going to draw a right angle for this field. And the rangefinder is 500 feet from the liftoff point. So here is my liftoff point. Here is my rangefinder. And it says it's 500 feet from the liftoff point, always 500 feet. So I'm able to actually plug that in. I don't need a variable there. That's constant. And then I've got my little hot air balloon. Okay. As I keep reading, at the moment, the rangefinder's elevation is pi over 4. The angle is increasing at the rate of 0.14 radians per minute. Okay, so at the specific moment when the elevation is pi over 4, angle is increasing at 0.14 radians per minute. So let's see if we can draw that out. The angle that we're talking about will be the angle from where you're at with the rangefinder to the balloon, going up like this. So I'm going to do theta for my angle. Okay, and we're looking like here. We have an angle of elevation. And from what they just told us, at the moment that the rangefinder's elevation is pi over 4, so when theta is pi over 4, the angle is increasing at the rate, so that would be d theta dt, it's a rate of change, increasing at a rate of 0.14 radians per minute. And those units are matching up, the d theta dt, so radians for theta measure and minutes for time measure. Okay, and then they want to know how fast is the balloon rising at that moment. So how fast balloon rising at that moment that we've been talking about. So we want, for rising, we want this information. Looking at kind of a coordinate system, I would probably call this y. You can label your picture however you want. But so we want dy by dt when, it said at that moment, when theta is pi over 4. Okay. So if this is what I want dy by dt, but it involves theta. So then I need an equation with y and theta. Can we come up with an equation with y and theta? Looking at this, since an angle is involved, some trig is going to be involved. And there are a couple different equations that you could write. You could maybe say that tangent of theta, and that would be y over 500, TOA, opposite, over adjacent. Or you could talk about cotangent. Instead of opposite over adjacent, you could do adjacent over opposite. So cotangent of theta would be 500 for adjacent over y for opposite. You need to think about, you're going to take derivatives. Which one is easier to take derivatives? Having this y in the denominator for cotangent is just a little more complicated. You could do quotient rule, you could bring the y up and think about it to the -1, but if you just work with the tangent formula, it's easier to differentiate. So as long as you have an equation that has the proper letters in it, you can pick which equation you want to work with and take your derivatives. So I'm going to clean this up and think about multiplying the 500 on both sides. 500 tangent of theta is equal to y. And then I don't need quotient rule. I don't even really need to deal with fractions. I can just deal with the 500 as a constant in front. And now I'm going to differentiate with respect to time. So that's an implicit idea. 500 is a constant. It hangs out in front. Derivative of tangent is secant squared. So secant squared theta, but with respect to time means I multiply by d theta dt. And then derivative of y is just 1, but with respect to time, 1 dy dt. And now I am specifically interested in dy dt when theta was pi over 4. So dy dt, drop the bar down when theta is pi over 4, is going to equal, well, 500 is a constant. Secant squared is really 1 over cosine squared. So 1 over cosine squared of pi over 4. And then times d theta dt is really 0.14, they told us. And so that ends up being 500. As far as this cosine squared pi over 4, go off to the side and do as much work with that as you want to. At pi over 4, cosine is square root of 2 over 2. You want that squared. So that's really on the bottom 2 over 4. With your double fractions, that really means 1 times 4 over 2. So this is really times 2. You don't need to show that work. You show as much of it as you need in order to get the right answer. But so 1 over cosine squared pi over 4 just gives us 2. And then we're multiplying by 0.14. And so that works out to be 140. And then as far as our units, dy by dt, y would have been measured in feet for the balloon rising. By dt was minutes here. So 140 feet per minute. Okay. Taking a look at our next example. A conical tank with vertex down is 10 feet across the top and 12 feet deep. So it's a cone. I have the vertex pointing down, 10 feet across the top, 12 feet deep. So if I draw that, a circle on top and then my cone coming down, 10 feet across the top, and then 12 feet deep. If water is flowing into the tank at a rate of 10 cubic feet per minute, so water is coming in at 10 feet cubed per minute, then they're starting to ask me a question. Find the rate of change, so I'm going to switch. Find rate of change of depth of the water when the water is 8 feet deep. So we want, and depth when you're dealing with these formulas is the h, the height part. So we want dh dt when h is equal to 8 feet. This 10 cubic feet per minute, looking at the units, cubic feet would be a volume measure. This is dV dt that they're giving me. So looking at those two together, can you come up with an equation with V and H. Well, yeah, the volume equation for a cone, the volume equation involves R and H. So V, for the volume part that I need, is equal to pi over 3 R squared H. I want it to have the V in it, I want it to have the H in it, and then just part of the formula is the R squared part. So here's my formula that I'm working with. If I were to differentiate right now, I would have product rule if I were to take my derivative. And actually, I think it's worth you taking a look at what that would be. So you would get dv dt, because you'd be differentiating with respect to time, would be pi over 3, and then the product rule, first times derivative of second, so r squared, and then dh dt, 1 for the h part with respect to time, dh dt. First times derivative of second plus second would be h. Derivative of the first would be 2r, but with respect to time, dr dt. And as you look at this, it's not that you can't do it, it's just that it's more complicated to have the product rule. And looking through at what you know, we know dv dt. Pi over 3 is just a constant. I don't know r. I suppose, given a height, I could figure out r, but they don't just come out and tell you. dh dt is what I want, so that would be good to keep in my problem. H, they tell me. But then back again, this r part, I could figure it out, but they don't come out and tell me. And dr dt, I don't know either. So looking at that, product rule was complicated, and there's some information that I don't know right off the bat. So this is a case where, if possible, try to make a substitution. And we're going to do similar triangles to replace r. Since I don't know much information about r. And how the similar triangles are going to work, look at the entire tank as one of your triangles, and I'm going to draw it larger, and then consider the tank as the water is coming up. So I'm going to draw that one with like the little ripple for the water to remind you. You'll have different triangles as the water is filling and filling and filling. So if you filled it all the way up, it would be 12 feet tall. And then across the top, it was 10 feet total, so 5 feet when you're just looking at the radius part. And then H and R for all the different representations working your way up to 12 and 5. Well, similar triangles work as, so 5 is to R, 5 over R equals 5 is to R as 12 is to H. And then if you want to cross multiply, 5H is equal to 12R. And trying to figure out what to solve for, if you want to get rid of R, then solve for R to replace. If I want to get R by itself, I'd have 5/12 H is equal to R. It will be easier when you differentiate to think about it as 5/12 H as that constant in front rather than 5H over 12. So back to my formula. Volume was equal to pi over 3 R squared H. So that's really pi over 3 times, I know what R is, 5/12 H, and you want to square it, pi R squared H. So, or sorry, pi over 3 R squared and then H. As you clean up, if this was a problem without a calculator, which very often they are, just some strategies. You don't necessarily want to merge everything. So I would think about this as volume being equal to my pi over 3, and then I would write it as 25 over 144. I wouldn't necessarily multiply the 3 and the 144, times h cubed, because you have the h squared from this portion, and then you have an extra h that was out to the side. So that's our volume formula. And now you're able to differentiate with respect to time. So with respect to time, you get 1 for the volume part, dv dt, equals pi over 3 and 25 over 144. Those are constants. And then the h part, 3h squared, but with respect to time, dh dt. And in this particular case, I can see already those 3's are going to cancel. So it's nice to have not put together the 144 and 3. And now let's talk about what we want and what we know. So we want, if you go back up and remember, we want dh dt with h being 8. And we knew from the given information that dv dt is always 10. So I can start plugging in information to solve. So I would have 10 being equal to the 25 pi over 144 as your constant, but then h squared, so we know h is 8, and then I want dh dt. And so now I just have to algebraically solve for dh dt. You might want to keep in mind that this 8 squared would really be over 1 as far as your fractions. You want to divide that whole constant piece right here, which really means you'd be multiplying by its reciprocal. So on the other side, you would have 10 times, and as you start flipping stuff over, you'd have 144 over 25 and your pi and your 64 when you square your 8. And so then that's equal to dh dt that you want to find. And the 64 is from the 8 squared. Okay, so without a calculator, some strategy there. If you want to multiply everything out and then reduce, you can, but you'll have smaller numbers if you just start trying to reduce what you have. For example, like the 10 with the 25, both divisible by 5. So I'd have 2 left on top and 5 left on the bottom. Well then, if you start to take a look, well that 2 with the 64, that would clean up to be 32 that would be left. So now on top, I just have that 144 part. Well, 144 and 32 are both even, so if you just start dividing by 2's, 144 cut in half is 72. 32 cut in half gives you 16. And then if you can remember, 8 goes into 72, and 8 definitely goes into 16, so divide by 8, you would have 9 left on top, 2 left on that bottom piece. And now as you look, the 9 on top, and then you have a 5 and a 2 on the bottom, and a pi. Leave the pi alone. But between the 5 and the 2 and the 9, you can't do anything else. So you now know that dh dt is going to be equal to the 9 that you have on top over 5 times 2, you have 10 pi on the bottom. And then our units, h for height or depth, would be measured in feet in this problem, and time in this problem is measured in minutes. So 9 over 10 pi feet per minute. Be very careful that this is not equal to 9 over 10 pi out to the side. The pi has to clearly be in the bottom of your fraction. All right. We're going to look at these next two just as far as setup. It's too long to solve 10 different examples out, but we do want to show you a fair amount of setup so that you're prepared to tackle new problems. So just to get this one going, a trough is 12 feet long, 3 feet across the top. They even drew you a picture. Its ends are isosceles triangles, altitudes of 3 feet. So they've got our picture marked. These ends that we're talking about, isosceles triangles, and then 12 feet going back like that. If the water is being pumped into the trough at 2 cubic feet per minute, so I'm going to redraw a picture so that we can kind of label some stuff that's going on. So if I redraw this triangle and then it's going back, I don't really need the part going back so much, but just so we know, we're filling up this water part, and water is coming in at 2 cubic feet per minute. Then they want to know how fast is the water level rising when it's 1 foot deep. So we want dH dt, because depth normally in our actual formulas equates to height. We want dH dt when h is 1 foot. And this 2 cubic feet per minute, the cubic feet is our clue that that's volume, so that's dV dt that I know about. So looking at those two together, can you come up with an equation with V and H? And they wouldn't necessarily give you the volume formula here. They might expect you to understand how to come up with it. So let's talk about that. Volume, like we talked about at the beginning, is just area of your base times your height. Well, in our picture, the base that we're talking about is the face of this triangle. That's the base as far as coming up with our volume formula. And the height that we are talking about, that would be like if you basically stood this out from the paper and kind of laid it on the triangular end. This is what we're talking about for height. And so it's really like the length, how far it goes back. So can I come up with a formula for the area of that triangular face? Well, yeah, you take the area of a triangle as just 1/2 base times height. And what we mean by that is like base going across this way, height for height of the water going up like that. And then again, we talked about in this particular case, L for our height there. So volume is equal to 1/2 times the base going across of the triangle, the height for the height of the water level, and then L for length back, depth going backwards. Then you want to think about, because right now if you start differentiating the base and the height and the length, that would be a really long product rule. Not that it can't be done, but it would be really long. So think about this situation. Is something changing? Are all the letters always changing, or is something constant? Well, the base, as you think about all the little baby ones filling up with water, that base is changing. It's getting bigger and bigger, or longer and longer as you get more and more water. And the height is definitely changing. But the length going back, that's the same in all of these. All of these would go the same distance back. And if you look back up at your picture, it was 12. So we can plug in that L equals 12 always. And if it's always the same, if it's always constant, then you can plug that in and get a much nicer formula to work with. So we would really have volume equal to 1/2 times base times height times 12. So volume is really 6 base times height. Still, at this point, you would have a product rule if you want to differentiate right now. And so this would be a time to think about if similar triangles would help you out, because product rule would get you a dB dt and a dH dt, but you don't really need the dB dt, or you don't really want the dB dt because you don't have information about that, but you're interested in dH dt. So try similar triangles and see if it works to help you replace. So if you draw your large triangle, assuming that you filled up the entire thing, they told you that was 3 across, and they told you it was 3 deep. And then if you think about one of your little baby ones with the water, just doing base and height. So 3 is to B as 3 is to H. If you fill it all the way up, not only is it an isosceles triangle, it's an equilateral triangle. And so when you multiply these, 3h is going to be equal to 3b. The height and the base is the same as you fill that up in ratio. So as you go through, you can go back up to your formula, and since you don't really care about the b in the formula, you know enough now to replace it. And you could go through and finish out solving. We just want to talk about setup, so picking out what's constant and what's changing. Okay, another setup. Construction worker pulls a 5-meter plank up the side of the building. So 5-meter plank, it's going up the side of the building by means of a rope tied to one end of the plank. And again, they drew us a picture. Assume the opposite end of the plank follows a path perpendicular to the wall of the building. And the worker pulls the rope at a rate of 0.15 meters per second. Let's see if we can draw all of that out. You can draw on that picture that they gave you if you want. I'm going to draw a little bit larger picture. So we've got the plank, and that's making a right triangle with the building and the ground because they said it was perpendicular. And it's a 5-meter plank that's never changing, so I can go ahead and plug that into my problem. And they're pulling the plank up the side of the building. As they're doing that, the base of it's going to get closer and closer to the building as well. And so if I have to start labeling things, I would go with like an XY plane. I would call the horizontal length X, the vertical length Y. And so if I read this rate of 0.15 meters per second, that's how they're pulling the rope. So we're pulling the rope to pull it up. So that would be dy by dt that they're giving you. And then they start to ask you a question. How fast is the end of the plank sliding along the ground when it's 2.5 meters from the wall? So they want to know this information. How is it sliding on the ground? So we want dx dt when it is 2.5 meters from the wall. So when x is 2.5 meters. So there's what I know. There's what I want. If I am interested in something to do with a length versus an angle, the length piece is going to tell me to try Pythagorean theorem. We saw a right triangle one at the beginning with the hot air balloon, and trig was involved there because we were talking about the angle. Here we're talking about the length. So the equation we're going to want to work with is x squared plus y squared equals 5 squared. The plank is always 5. So I'm allowed to plug that in. And then I can differentiate with respect to time. So differentiating with respect to time, I would come up with 2x with respect to time, so dx dt, plus 2y with respect to time, so dy dt, equals, differentiating constants is always nice, they go to 0. And just as a heads up when you're working these, because you'll work a fair amount with Pythagorean theorem, notice those 2's all the way across. You could divide all the parts of your equation by 2, leaving you with x dx dt plus y dy dt equals still 0 because 0 divided by 2 stays 0. So that cleans it up where you will get some smaller numbers to deal with. And then we're just talking about setup. So going back to what they want, as we start plugging everything in, we want dx dt when x is 2.5. So we knew that the x part was 2.5. We want the dx dt, we don't know it yet, plus the y, they didn't tell us anything about y, but they did tell us that dy dt was 0.15. So I can plug that in. And I'm interested in this dx dt, so it's okay to have that there. But having this y there is a problem So you need to figure out what to do with the y, how to get rid of it, what it is, what it equals. So basically, we need to solve for y when x is 2.5. So look at a special case of that triangle. Not all the time would this be true, but at this instant, x is 2.5, the plank is still 5, and we want to solve for y. So we would have 2.5 squared plus y squared equals 25. And so y squared, when you clean it all up, is 18.75. And then you're going to plug that in. Well, you're going to square root it first. So y would equal plus or minus square root of 18.75. And we're not going to deal with the minus case here because in real life, for the height there, it's going to be positive. And now you're going to plug in and solve. So again, just set up just so that you're exposed to a few more problems. You'd have to finish that one out to get an answer. Last one, shadow guy. Shadow guy is a classic related rates problem. You're going to see him over and over and over again. Any calculus textbook, any AP test, any calculus class across the country. So we have the guy, the man. He is 6 feet tall, and he walks at a rate of 5 feet per second, in this case away from the light. The light is 15 feet above the ground. And again, they drew you a picture. Then they're asking you when he is 10 feet from the base of the light, so not always, but in this instant, when he is 10 feet from the base of the light, they're going to ask you some questions that are down below. In both cases for these questions, the same picture will work, so we're going to translate what we know. So our guy up here is 6 feet tall, we know, and the light here is 15 feet tall, we know. I'm going to redraw that so I can have a larger picture to deal with. So big right triangle with the 15 for the light and the 6 for the guy. And then just so that we're all on the same page, here is the marking of the shadow. Okay, this would be his tip of his shadow. And in this case, the guy is walking away from the light. Sometimes you'll see them where he's walking towards the light. And they actually told us a rate as well. He walks away at a rate of 5 feet per second. So if I start labeling kind of like we've been talking about, I'm going to call this x, going from the light to the guy. And so then this is telling me that dx dt is 5 feet per second. So that's all the information I know. Then they're going to ask me specifically when x is 10 feet. We can deal with that in a moment. Okay. As we go and look at the questions down below. At what rate is the tip of the shadow moving? And they're talking about away from the base of the lamp. At what rate is the tip of the shadow moving? So let's figure out what we want there. So what we want there, I'm going to redraw so that you can see two separate triangles rather than them being nested. So looking at our original picture and breaking it apart a little bit, you would have one very large triangle with the 15 for the lamp, and then you would have the smaller triangle with the 6 feet for the guy. And we talked about the distance from the lamp to the guy was x. But that doesn't cover, that covers like up to here, but not the whole length. Let's go back and label some more of this picture. So you can pick another letter. You could do X and Y if you want. I usually do Y for height. So I'm going to do X and Z. So I'm going to break this apart down here to say that this piece is X and that this second piece, what's left, is Z. So then that means the entire piece is X plus Z for the whole thing. You can pick whatever letter you want. So then down here for the large triangle, I would have x plus z for the whole thing. And for the small one, just with the guy, I would have z. Okay, so I have the two triangles. And what I want, if I want to know about the tip of the shadow, but I am talking about it from the base of the lamp. So we measured in the picture up above that this is the guy's shadow, but the tip of the shadow is actually present in both pictures. If I'm talking about the tip of the shadow moving away from the base of the lamp, then I want d by dt of that longer one, of x plus z. I want the derivative with respect to time of that long side, the long triangle. And we know derivative rules let us take derivatives one at a time when we're adding and subtracting. So really, I want dx dt plus dz dt. Well, in order to make that happen, I need an equation that's relating the x with the z, and the 15 and the 6 and all of that. Well, that's a similar triangle idea. So coming back up here, I would do your equation work up here because it's going to be translated for any question that they're going to ask you. So we could say that 15 is to 6 as x plus z is to z. And then we can cross multiply. So 15z is equal to 6x plus 6z. You have to distribute. And group like terms on one side. So that means we really have 9 of the z's equals 6 of the x's. In the problem, if you notice, they already told us dx dt. We already know that. I don't know dz dt, so I'm going to solve this for z. So z is equal to 6/9 x or 2/3 x. Z equals 2/3 x. And because of that, then if I differentiate, dz dt is equal to 2/3 dx dt, differentiating with respect to time. So now I know about all the pieces because they told me about dx dt, and in this question I know that I need dz dt. I've now figured out everything I need to know. So to answer part A, I want dx dt plus, and I just solved for dz dt, so 2/3 dx dt. And then going back up to the beginning, they told us that dx dt was 5. So 5 plus, and then put 5 in over here for dx dt as well. So to solve this out, I really have 5 plus 10/3. And 5 plus 10/3, 5 is really 15/3, so I have 25/3. As far as units for the x plus z to change, that would be a length, so feet, with respect to time, seconds. 25/3 feet per second. And then at what rate, they're asking me another question, is the length of the shadow changing? So in that case, if you go back up and look at just the length of the shadow, I can look at just the smaller triangle. I really just want dz dt. Well, I solved dz dt up above. It was equal to 2/3 times dx dt. And I know dx dt, so it's really equal to 2/3 times 5, so 10/3. And then as far as units, z would be a length as well, so feet. And again, time in seconds, feet per second. Something that's interesting about this question and about all of the shadow guy questions, they were asking us when he is 10 feet from the base of the light, so when x is equal to 10, they were asking us these different questions. But if you notice in both of the solutions, I never had to plug in a plain x. It always just boiled down to dx dt and dz dt. So it really didn't matter how far the guy was from the light, how close he was from the light. It just matters how fast he's walking for all of those rates of change. Again, this is a classic one, just going back to right triangles and similar triangle, not right triangles necessarily, but similar triangle relationships. All right, that's 2.6. Now you need to try to practice.